I did not get quite as far as I had wanted to in making out these notes, so we're probably going to wind up ending class slightly earlier than I had anticipated, so that I don't just keep going and confuse the hell out of everybody trying to wing stuff here. So we are going to be talking about filter design today, and we are going to be restricting ourselves to what I developed the table for. Yes, sir.
Like 4 times reading through all the posts, and I still feel like I'm foolish. What is the best way to study for all this stuff?
So for this upcoming test, it would be to do the homework assignments that I have yet to give you. Let's talk about that really quickly. It is my goal to get your homework assignment for the remainder of the class up tomorrow. I am also seriously considering just doing a take-home exam for exam 3. That would effectively just be like homework problems, but all smashed together into one thing, so that you'd have, you know, roughly a week to work on stuff, ask questions and all that kind of jazz, so that you are not being penalized for my having so much shit to do that I forgot to put homeworks and stuff up. However you want to put that nicer, do that. Is anybody vehemently opposed to that idea?
I like that idea.
Okay, most people seem to like that idea. I got no beef with that. If you guys don't mind it, it'll be less giving me panic attacks as well. So let's go that route. So exam 3 will just be take home stuff. Does that alleviate any of your concerns, Nicholas? Okay.
When would you post the take home exam?
I'm going to try to have everything tomorrow. Worst case scenario, I can get, so I have like, I think 3 of the 4 circuits that I want you guys to analyze for homework set number 7 already drawn. If you will allow me to not post the solutions, I can probably have that up, or not give you the answers. I could probably have that up this afternoon. The second homework set, I haven't even, or homework set number 8, honestly haven't even begun to think about yet, but I feel strongly that I can get it finished tomorrow afternoon. And then with regards to the exam, it would be just finding other problems similar to what I'm putting on homework set number 7 and what I'm putting on homework set number 8. So I don't think that'll take me much longer after I get homework 8 finished. So the goal is to have the homework sets up to you guys by tomorrow, and then probably the exam by Saturday afternoon at the absolute latest. I can see what I can do. I will very likely put them out with the answers to be determined, and then work on getting those answers figured out this weekend, and then re-upload once I have those things figured out. Okay? So that you have more time to at least get started. You shouldn't be just waiting on me to provide you the answers, in my opinion. Just to be real clear here, I'm in no way, shape, or form required to give you the answers for anything. But I'm trying to not be an ass about things, because if I give you the answers, it means there's less of you in my office asking me questions, which means I technically should be getting slightly more work done, but it never works out that way. Yeah, so everything will be officially due Thursday. Unofficially, I would like to have it by Sunday at midnight, so that I and my graders have time to actually look at stuff. And I need to double check to make sure that, I think grades are due on Tuesday, but if they're due on Monday, we need a little bit more lead time, so it might be due Saturday at midnight instead of Sunday at midnight, officially, kind of, or unofficially, whatever. Yes.
Is there
For sure. So right now, your exam 2 in-class portions have been graded, and your exam 2 take-home portions. I spent the last 30 minutes trying to figure out. So for problem 2, you guys have got an answer that's different than mine, or the overwhelming majority of you guys have an answer that's different from mine. I cannot find the error in your work, nor can I find the error in my work, because we're literally putting the exact same equations in the math pad and getting different results. So I'm getting real pissed off right now. Huh? I don't think so. And to be clear here, I honestly believe that you guys are correct and it's not me. And the reason why I say that is because I'm getting a fifth order polynomial. And that doesn't make sense because I should have one thing for the unit step function. I should have one thing for the simple exponential, and then I should have a second order equation because I have two energy storage elements. So I should be getting a fourth order polynomial, which is exactly what you guys are getting. Somewhere I'm getting an extra term that doesn't make a damn bit of sense to me mathematically. But I cannot figure out where the mistake is that's fixing that, North.
I had the issue when I was solving it in practice. I don't know what yours looks like, but when I put a fraction,
Okay, so I might need to look at fractions then. All right, thank you for that. So when you say fractions, so in my system, like the only fraction that I would have would be like 0.5 s. So you're saying put in 1/2 s?
for the shot.
Okay.
Mine wasn't as clean a number, so I think it was rounding, but.
Okay.
Well, what that would do with it, I gotta try to understand, is I would put in 1/f, let's say, 0.1.
Mm-hmm.
I would have 1/0.1s. Would give me a different polynomial answer than if I did 10/s.
So I tried switching that in mine and I was getting, so I did 1/0.5 s as well as just 2/s and got the exact same result either way.
Well, I wouldn't want it different.
No idea.
Mine also did that, but we were equivalent. It was just like one kind of a constant factor out versus the other.
Yeah.
Nick, I think you had your hand.
0, I wanted to say when I approached something 0.5, when I changed it.
Okay. I will look into that because yeah, I saw you guys' work, cannot find an error. Also can't find an error in mine because it's three pretty easy mesh equations. And so I'm just completely and utterly baffled as to how we're getting different results. But I firmly believe that you guys' answer with the fourth order polynomial is correct because that's the thing that actually makes sense given what the system looks like. So if I can't get it sorted out, honestly, I'll probably just say, well, this is the correct answer because 70% of you got it, and then just deal with it from that standpoint. But I would like to know why my answer is wrong, which, you know, I hope I've made it very aware that I'm okay with admitting my mistakes and all of that kind of good stuff. All right. Anything else before we do stuff? Sounds like the answer is no. All right, let's do stuff. All right, so today we are going to talk about passive filter design. And explicitly, we are going to look at Butterworth filters. So all right. So for most higher order filter designs, we are going to have the option of dealing with either a Butterworth filter or a Chebyshev filter. So Butterworth filters are characterized by their completely flat response in the pass band of the filter, whereas a Chebyshev filter has a ripple response in the passband. Okay. And the reason for these responses is attributed to the quality factors of both filters. So Butterworth filter is a medium Q filter. Okay. So it represents kind of a middle of the road design constraint where it gets the job done, but it may not be the most efficient way to necessarily do things. It might not offer the best performance. So with medium Q, that typically means that we are going to have a wider bandwidth. So if we're trying to devise a, let's say, a band pass filter, that means that our pass band is going to be wider and it's not going to provide the rejection that we need for certain applications. If we need to pass wideband signals, a Butterworth filter is great. A Chebyshev filter, alternatively, is a high Q filter, meaning that it offers very high selectivity, so very narrow bandwidth and all of that kind of good stuff, which for some applications is also required, and for other applications is exactly what we don't need. So that's the reason why we kind of choose between these two particular forms based on the application that we need. So today we're going to look at Butterworth filters, and we're probably going to get through high pass. We're going to do lots of stuff with a low pass filter because that's what the sheet thing handout that I gave you guys is all about. And we're going to talk about how we can use our understanding of our low pass filter tables to develop high pass filters. And then on Friday, we'll use the exact same tables with that low pass topology to do band stop and band pass. So if we have a very good grasp on how to implement a low pass Butterworth filter, everything else is just one simple iteration from that. So that's why we're focusing so much on this. Just as a quick thing, if I were to plot the responses of these two filters on top of each other, where this is my transfer function h of j omega, this is going to correspond to 0 decibels. Let's put negative 20 dB here and negative 40 dB here. Let's put our corner frequency here. For the Butterworth filter, I would have something that looks like this. I'm starting at roughly negative 6 decibels, and we'll talk about why in just a second. So it should roll off at 40 dBs per decade. So something like this. This doesn't look very flat, but it's supposed to be. And then I'm going to call this Butterworth with n equal 2. So that's the filter order. And then for the Chebyshev, it would also start at negative 6 decibels. It would tend to dip down, come back up, overshoot, and then get back to that negative 40 dB per decade response that we would expect for a second order filter. So again, we have very flat response in the passband with the Butterworth, which is exactly what it was designed for. Or with the Chebyshev, we see that we have very high Q around our resonant frequency, giving us great selectivity. The only problem with that is that we see that below our corner frequency, we also have a drop off, and we can design for a particular ripple, as it's called, to try to minimize that, but that increases component values and all that kind of jazz. So we'll talk about that probably on Friday. All right, so here's the kind of background for what we're dealing with. Let's talk about Butterworth filters specifically. So the attenuation provided by a Butterworth filter is given by the following relationship. So the attenuation measured in decibels is 10 times the log base 10 of 1 plus omega over omega c to the 2n power, where omega is our frequency of interest, omega c is the cutoff frequency for our low pass filter, defined to be the frequency at which our attenuation is exactly equal to 3 decibels. And n is the order of the filter. So if we wanted to determine what is the minimum order required to achieve at least 50 decibels of attenuation at a frequency of 150 megahertz if the filter cutoff frequency is FC, so linear frequency, 50 megahertz, right? So this is a design constraint, effectively. We want to design a filter that achieves at least 50 decibels of attenuation when our frequency of interest is effectively 3 times as large as our cutoff or corner frequency, okay? So the first thing that we need to know in order to design a filter that meets this criterion is what order filter that we're going to implement. So how many energy storage elements we're going to need. So I'm just going to simply use my attenuation relationship up here and figure that out. So my attenuation is 50 decibels. So I'm going to have 50 is equal to 10 times the log of 1 plus. So now I'm going to put in the ratio of my frequency of interest divided by my cutoff frequency, right? My frequency of interest is 150 megahertz. My cutoff frequency is 50 megahertz. Technically speaking, we're dealing with omegas here, but the 2 pi's are going to cancel each other out, so I don't need to worry about that. The ratio of the frequencies is going to be the same either way. So it's looking like I'm at 3 to 1. So this is going to be 3 to the 2n power, all right? So now I'm going to divide both sides by 10. So 5 is going to be equal to the log of 1 plus 3 to the 2n. I'm going to get rid of that logarithm by having 10 to the on both sides, right? So 10 to the 5 will be equal to 1 plus 3 to the 2n. 10 to the 5 is a really large number, so I'm going to effectively ignore that 1, right? Because 100,000 is equal to 1 plus something is going to be effectively the same as 100,000 is equal to something. So 3, that 3 doesn't look particularly 3-like to me. And to go even further, 3 to the 2n is the same thing as 9 to the n. So based on this relationship, what do you think my minimum filter order is going to be? So you're saying that 10 to the 5 is equal to effectively 9 to the 5. I disagree with that slightly, yeah. So chances are it's going to be, well, and not chances are, it's definitely going to be greater than 5. And my filter order literally cannot be not an integer, because my order is telling me the number of energy storage elements that I have in my system, right? So it has to be an integer. So I'm going to guess 6. So n needs to be greater than or equal to 6. If I solve for n exactly, I wound up getting 5.24. So this is a pretty reasonable estimation. It worked out prettily because 150 over 50 is 3 and 3 squared is 9. So it was a pretty apples to apples comparison. If it weren't, you might actually have to use a calculator to do this estimation. This was fairly straightforward. Okay. So we're going to need at least a 6th order filter in order to get this amount of attenuation for this particular frequency. All right, so now let's use our table. Yes, Hannah. So let me go back to my graph here. So let's say that this omega c right here is 2 pi times 50 hertz. 50 megahertz. So somewhere about, let's see, right here would be 3 omegas. So if I know that this was -6 dB, at this point right here, I'm looking for something that would be -56 dB so that I have 50 decibels of attenuation. My signal strength is 50 decibels lower than what it was at my corner frequency, right? So I'm going to need a fairly high order filter in order to cause my frequency response to roll off that quickly, right? A 2nd order filter got me there, means I'm going to roll off at about 40 decibels per decade. I'm looking for 50 decibels of roll off in 1/3 of a decade. So I'm going to need a pretty high order filter in order to have that happen. So the higher the order of my filter, the steeper this roll off is going to be. So for like n is equal to 100, it would be pretty damn close to a brick wall filter response where it's going to fall damn near instantaneously, because I'm going to be having, let's see, so 100 would be 200 decibels per decade. No, 2000 decibels per decade of roll off. That being said, that would mean 100 energy storage elements. That would be a monstrous thing to ever implement. It would be rather expensive too. And also the math would suck. Yes.
Doesn't it matter if you end up with like holes or like if there's just one drop off? Or...
So fantastic question. So for this Butterworth filters, actually, so a mathematician, the filter isn't a Butterworth thing. We're going to see that in a moment. It's just a series, like we're effectively going to have the exact same topology for a Butterworth filter as a Chebyshev filter, as a Bessel filter, if we got into that. It's all a question of what our component values are going to be. And so what we're actually doing is using component values to solve what's called a Butterworth polynomial. And a Butterworth polynomial is just a polynomial in which we have it repeated, the pole repeated n number of times. So we are explicitly having our pole here a whole bunch of times in order to give us that extremely steep roll-off. Similar thing with a Chebyshev filter, except that we need to also take into account that we want high Q. Yes.
If you take a
butterworth, and say it has a, or we think it's high, really low, would that not fire?
So Q is all about energy storage over energy dissipated. So high Q means we would have a resonance peak. We would see an uptick here. Satisfying the Butterworth polynomial, specifically, this was designed to have a flat passband. So it's always going to have a lower value of Q because that's what the polynomial was designed to describe. We want it as flat as humanly possible in the passband and then to roll off as abruptly as possible based on the order of the filter. Any other questions? Yes, ma'am. How did I know what was -6? Oh, so I'll show you that right now when I draw the circuit. That's why I'm starting off with -6 decibels. Okay, so filter topology that we're going to use, and it's also provided to you on your handout sheet. We can use one of two different topologies. Right now, when we're dealing with RS is equal to RL, they're both equally as good. And we're going to get effectively the same component values, just in slightly different order. Okay. So let me draw this thing out real quick. So I'm going to start with this one here, where we have a capacitor in the element 1 position, right? So we have 1 ohm, and then we have our capacitor C1. This will be our second energy storage element, so that's why it's getting the subscript 2. Here's our third energy storage element, subscript 3. Our fourth energy storage element, so subscript 4. Our fifth energy storage element, so subscript 5. Our sixth energy storage element, so subscript 6. And then here is our load. We're going to normalize this so that we have 1 ohms at the load and 1 ohms at the source. So let's talk about where that -6 decibels came from. Okay, fantastic question. Yeah. At very, very low frequencies, like approaching DC, what do all of these capacitors look like? Open circuits. What do all these inductors look like? Short circuits. So for very, very low frequencies, this is just a simple voltage divider where the voltage is being dropped evenly over these two 1 ohm resistors that are effectively in series. Our output voltage is therefore 1/2. What's 20 log of 1/2? -6 decibels. There we go. So that's where the -6 comes from. Did you get that? You shook your head no, and then you said yes. So I'm quite confused. You didn't. Okay, that's okay. So all of these capacitors at very low frequencies are open circuits. All of these inductors at very low frequencies are short circuits. So what this looks like at a very low frequency is our source connected in series with a 1 ohm resistor, connected in series with a 1 ohm resistor. Because all these are shorts and all these are opens. So the voltage dropped across this 1 ohm resistor, which is where our output would be taken, will be exactly half of whatever our voltage source supply. 20 log of 1/2 is -6 dB. All right. So this is one topology. The other topology that we could use is effectively the same thing, except that we're going to start with the inductor in the first position. So here we have L1, C2, L3, C4, L5, C6, 1 ohm resistor over here. So we can choose which of these two topologies to use. Completely interchangeable, and as we'll see here in a couple of moments, we're going to have the exact same inductor values for both and the exact same capacitor values for both. So there is literally no advantage of using one over the other because it requires identical number of components, identically sized components, and their response is also literally identical. So it does not matter which one we choose. Yes. Yeah. So my first energy storage element has a subscript of 1, my second 2, my third 3, 4, 5, 6. First element 1, 2, 3, 4, 5, 6. Just done that way in particular so that we can make sense of this table that I have provided to you guys. All right, so we want to design a 6th order Butterworth low pass filter that has a corner frequency of 50 megahertz. Let's also give a constraint. We want RS to be equal to RL to be equal to 50 ohms. So we have 50 ohm termination on the load side, 50 ohm termination on the source side, which is exactly what we'd be able to reproduce upstairs using an oscilloscope and function generator and all that kind of good stuff. Okay. So let me pull up our table here. So open Dropbox 224 low pass filter tables. So we have a 6th order filter. So that means I'm going to go to n is equal to 6. And these are the component values that I'm going to have. If I'm using this topology, which is with the capacitor in the element number 1 position, I read the table going down. So C1 will have a value of 0.518 farads. L2 will have a value of 1.414 henries. C3 will have a value of 1.932 farads. L4 will have a value of 1.932 henries. So all of these C's are expressed in henries, farads. All of these L's are expressed in henries. Now, if instead I choose to implement my filter utilizing this topology, I read my table going up, which means L1 will have a value of 0.518 henries, C2 will have a value of 1.414 farads, and so on and so forth. So that's how we use the table. If we're using this topology, this tells us the value of our element, C1. If we're using this topology, we look out this way, and so L1 will have this value. Yes? So we are going to wind up scaling things like we did in our last class, right? So right now we have a normalized system where we have 1 ohm at the source and 1 ohm at the load, because we're designing a system for a 50 ohm resistor at the source and a 50 ohm resistor at the load. That means our magnitude scaling factor is going to be 50, right? Our frequency scaling factor is going to be 2 pi times 50 megahertz divided by 1 radian per second is just 2 pi times 50 megahertz, or pi times 10 to the 8 megahertz. So we'll get to that in just a second though, but I want to make sure that we're all clear on how to use this table. So, Justin, are we going to use this topology or this topology, top or bottom? Bottom, okay. So we're gonna start with this guy right here. Get this out of the way. All right. So since we're starting with this topology right here, just reading off of my table, L1 should be 0.518. Henries. C2 should be 1.414 farads. 1.932 Henries. 1.932 farads. 1.414 Henries. 0.518 farads, right? So this is what our normalized filter is going to look like, designed specifically to have a cutoff frequency at 1 radian per second for using 1 ohm resistors. So as I mentioned a moment ago, I don't know. I want that thing at the bottom to go away without, well, that closed out LT Spice. I'll be there. All right, I'll have to turn it back on in a moment. So based on our design criterion, our magnitude scaling factor is going to be 50 ohms divided by 1 ohm, just 50. Because in our table, we're dealing with 1 ohm resistors and we want this to work for 50 ohm resistances. And we're also going to have KF is going to be 2 pi times 50 megahertz divided by 1 radians per second. So 2 pi times 50 is 100 pi. So 100 pi times 10 to the 6th is pi times 10 to the 8th. So these are my scaling factors, right? So from here, I can see that L1 prime is going to be Km over Kf times L1. So that is 50 divided by pi times 10 to the 8th times 0.518 henries. Comes out to be 82.442 nanohenries. C2 prime is going to be C2 divided by Km Kf. So that is going to be 1.414 farads divided by 50 pi times 10 to the 8th. That looks too much like 108 for me. So that comes out to be 90.018 picofarads. And using the exact same relationships, we'll find out that L3 prime is 307.487 nanohenries. C4 prime is 122.995 nanohenries. Excuse me, nanofarads. Picofarads. Just losing my damn mind up here. Thank you for that. L5 is going to come out to be 225.045 nanohenries. And C6 prime is going to be 32.977 picofarads. So let me bring LT Spice back up real quick. So what I have here is this is the topology that was on the top of the sheet. This is the topology that was on the bottom of the sheet. I just did both just in case you guys chose what I wasn't expecting. So if I simulate this, let me get this dumb thing out of the way. Actually, before we even simulate it, notice that the component values are literally the exact same thing. They're just swapped around, right? So for the capacitor and the lead-off position thing for our inductors, we go 225, then 307, then 82.442. They're just in the opposite order here. For the capacitors, we go 32.997, then 122.995, then 90.018. They're just in the opposite order here. It's literally the exact same components, regardless of which way we do it. So simulating this, looking at the output here, changing the color to not be green. Just need to make that not the default. Okay. Let's click here. So we're looking for where our magnitude is -9 decibels. There we go. We can see that it's slightly lower than -9 dB, which is 3 decibels lower than the -6 dB threshold we have at pretty damn close to 50 megahertz, which is exactly what we wanted to have happen. If we look at this thing here, so let's see. So at 1 gigahertz, we are at -160 dB. At 10 gigahertz, we are at -280 dB. So we have decayed by 120 decibels in a single decade, which would make sense for a 6-order filter because it should be 20 decibels per decade for each order. Okay. So this is exactly the response that we would expect. So let's see, so at 50 megahertz, we're at -9 decibels. Let's look at what's going on at 150 megahertz to make sure this attenuation was at least 50 decibels, which is what we were originally designing for. So at a little over 150 megahertz, we are down from -6 to -63, which is about 57 decibels of attenuation, exceeding what our design constraint was, right? So everything seems to have worked out there. Just for the sake of argument, let's look at the response here at this node. Let's change it to red. It is literally the exact same response. Like literally the same thing. So it 100% does not matter which of these two topologies we choose to utilize. It has the exact same frequency response, the exact same number of components with the exact same values. Again, there is literally no advantage to one over the other. That will change in a moment when we talk about what happens with RS is not equal to RL. All right, so before we move along to that, any questions about using the table? Yes. So if we're using this table, let me go to the table here. This table is explicitly defined such that omega c is 1 radian per second and RS and RL are equal and have a value of 1. If we wanted to develop a table for a different corner frequency, we would simply frequency scale all of these values. If we wanted to develop a table for this frequency, but a different value of RS or RL, we would magnitude scale all of these values. Any other questions about this? All right, so on occasion, we will need to design a filter that works when RS and RL are not the same. Which brings us to our second table, which actually is so big that it takes 2 pages, and I was only able to get 7 orders of stuff on there, which is realistically more than you'll ever need. We have the exact same topology, except that now I'm explicitly saying that RS and RL are not the same, but we are setting RL to be equal to 1 ohm. So we have this new column right here that gives us RS over RL as a ratio. Notice that for even orders, the table is giving us increasing values of RS over RL. And then for odd orders, the table is giving us decreasing values of RS over RL. If we scroll down to the bottom here, for the other topology, reading the table up, we look at RL over RS. So effectively, things are going in the opposite direction. So let's say that we wanted to repeat our previous design exercise, except that we want RS to be 50 ohms and RL to be 500 ohms. So I'm going to scroll down here to the 6th order filter bit. I'm going to write off here to the side that RS is 50 ohms and RL is 500 ohms. So that means RS divided by RL is 1/10, or RL divided by RS is 10. So I would argue that to achieve this filter design specification, this is the row on the table that we should be using, yes, sir. So not anything that I'm going to give you, no. So realistically, you would just find the ratio that's closest and call it a day. Yeah. So anything over 100 to 1 is just the infinity thing. Like that's such a large difference that just use this. Anything else, just find it that's closest, but I'm going to explicitly choose numbers so that you can read directly off the table because I'm going to try to be less of a jerk. All right, so RL over RS is equal to 10, so that's why we're using this thing, and we would have to use this particular topology because it's the one that matters when we're looking at a particular RL over RS value. So because we have an even ordered filter, we wind up having to use this one because RL is greater than RS. If we had an odd ordered filter where RL was greater than RS, we would wind up using the one with the capacitor in the front. So once we start dealing with non-equal terminal impedances, we actually have to pay attention to which one of these we use. With regards to our scaling factors here, so Km would be 500 ohms divided by 1 ohm is 500. It is based off of the load resistance being scaled to 1 ohm, right? And the source resistance is just whatever the hell it happens to be for that scaled system. KF would be the exact same thing as it was before. So 2 pi times, 50 megahertz divided by 1 radian per second is going to give us pi times 10 to the 8 as our scaling factor. And from this point, it's effectively the exact same thing we did in the previous example. We just use these scaling factors and these values from our table in order to make everything work out. I had every intention of simulating that circuit, but then people came to my office hours like real jerks, and so I didn't get a chance to do it. So we're just going to move past that. Okay. So this is how we use the table when we have non-equal impedances on either side of it. Any questions about that? Fairly straightforward. Yes, Brody. Yeah. Yes. So explicitly, these table values are valid when RL is 1 ohm. And RS is just whatever it happens to be, with scaling the load resistance down to 1 ohm. Once again, we could make a different table if we wanted to by scaling all this stuff, but this is what I got, so that's what I'm using. All right. So we have 15 minutes left, so let's talk about high pass filters for maybe 3 or 4 minutes and then call it a day, because this is the end of where I'm prepared. All right. All of these tables that we have developed thus far are for making a low pass filter. In order to make a high pass filter, let me scroll up to the very beginning. We will talk about this process. Okay. I'm going to replace this capacitor with an inductor, and its value will be 1 over C1. I will replace this inductor with a capacitor, and its value will be 1 over L2. So on and so forth. We simply replace our inductors with capacitors, replace our capacitors with inductors, and then we use the reciprocal of whatever's in the table. So that's high pass filter design. If we know how to use the tables for our low pass filter, we can easily get a high pass filter. What we'll see on Friday is that to get a band pass filter for all of these shunt legs, we're going to replace it with a parallel connection, having an L and a C using the table value, and all of these horizontally oriented things will have a series connection with an L in series with a C, using the exact same value. And then to get a band stop filter, we do series here and parallel here, or whatever the hell the opposite is. And we'll go into examples and all that kind of stuff to illustrate it. The design there or using the tables is a little bit different because we're no longer necessarily looking for, effectively the bandwidth of the filter is going to be the same thing. The bandwidth of the band stop filter or band pass filter is going to have the same value as the cutoff frequency for one of these. So we have to talk about how to design for specific cutoff frequencies, which I'm not ready to do with any level of confidence yet. All right, so this is our first talk on filter design. Yes.